Hi, so I'm here today to talk a little bit about machine learning with a specific focus on neural networks. I've only got 5 minutes, so without further ado, let's get right into it. So I just wanted to talk quickly about the two fundamental types of machine learning, and that is supervised learning and unsupervised learning. So supervised learning is where the training data is labeled. So what we mean by this is for a given set of features or inputs, we have a desired set of outputs. So saying, look, if I give the algorithm this set of inputs, I want these set of outputs to be, returned to me. So it's examples of the correct answer is provided if you like. So this includes algorithms such as regression and classification. On the other hand, we have unsupervised learning, where the training data is not labeled. There's no inherent or obvious solution. There's no correct answers for a given set of features. So instead, the algorithm tries to find patterns for each of the features or clusters. So as we can see, these algorithms include clustering and anomaly detection. So, okay, the neural network model. So the neural network model is loosely inspired by the way our brain works and how we have millions and millions of neurons all connected by these things called synapses, which is these lines that you can see here. But basically, it works upon the principle that these neurons in our brain, they send signals to each other, and based on these signals, a function or procedure is undertaken when the signal is received. So we have an input layer. So this is what our features are going to be fed into. So the input layer, the amount of nodes in the input layer is always equal to the amount of features you have. And then you have the hidden layer, I'll get onto that later, and then we have the output layer. So the output layer is just where you're getting your outputs based on the features you've inputted. So the hidden layer, that's responsible for the complexity, if you like. So as we can see when I go onto full propagation, the more hidden layers you have, you can think of the neural network as a black box almost. It's all this string is trying to create a classifier or a function rather to map your desired inputs to a desired set of outputs, right? So the more hidden layers you have, it's going to be the more complex functions are going to be able to be achieved. So we have these things called synapses. So all these synapses are going to contain a weight, which is just a numerical value. And then we have these neurons, which act as a unit of computation. So all neurons, with the exception of the input neurons, have something called an activation function. And what this does is introduces non-linearity into the model. So this allows, if your data set is non-linear, this allows the neural network to be able to model that, as we'll get into later. So we have the forward propagation algorithm. So the forward propagation is the procedure by which we obtain an output from a given set of inputs. So basically, we initiate the weights on each synapses at random values close to zero, and then we have each feature almost sort of travels along that way. So when it travels along that way, it's multiplied by that way. So if you see here, x1 becomes red because it's been multiplied by this way here. So for example, this could be a 0.5, and this new x1 apostrophe just represents 0.5 x1. And then we have the other connection is x2. So x2 has also been multiplied by this orange way here. And then we apply the activation function to the summation of both of the neurons that are feeding into this later neuron to get that output, and happens with the other layers, and so on and so forth. So the neuron in this hidden layer here, so the output of this function is going to be multiplied by the weight on this synapse, and then so on with this, and then that's going to compute one. And we do this, and we continue this procedure until we get a given output. So, but what good is this if we're just giving nonsense output? How is this helping? Enter backpropagation. So what we do is we establish something called a cost function, and this is sort of a mathematical way of rewarding the algorithm. So the cost function we use is something called the sum of the squared errors. So y here is the real value, what we want to be achieved, and y hat is the output given by a neural network. So as you can see, if your output is close to what the real answer is, this cost function overall is going to be low. So it's almost rewarding the algorithm for giving correct answers. But on the other hand, if the output is very high, if the difference between them is very high, then it's going to be reflected by a very large value in the cost function. So our overall goal is to minimize the cost function because this means that we've achieved a combination of weights that has successfully mapped our inputs to our outputs. So the intuition behind backpropagation is, after we perform forward propagation, we get some output, and we look at that output and we say, okay, I want this output to be closer to the real value for that given training example. So how can I change these weights right here to make that output closer to what it should be, right? So we calculate something called the errors in that layer, and then we take the same procedure and we apply it to that subsequent layer. So we look at these weights connecting to these ones. It's like, okay, how can I make that closer to what I want this to be? And we follow this backwards and backwards, and we keep going. So that is, to be honest, quite frankly, how the backpropagation algorithm works. We have the communication between this. It's like a backwards procedure, traversing backwards, in order to find how we can modify these weights, and we keep making these adjustments over, and we iterate over the training examples until we found a combination of weights that successfully map our inputs onto our desired outputs. So let's get into some applications now. So one big application of neural network is image recognition, and this has become successful because of a specific type of neural network known as a convolutional neural network. So this is a type of deep learning, which means it has many hidden layers, which allow it to, make very complex functions. So the way this convolutional neural network works is basically with each layer, some sort of feature is being extracted from the image. So the first layer might be looking at the sort of the edges of the image. The second layer might be looking at specific, colors in the image. The third layer might go even more complex into being able to analyze specific objects in the image, right? And then so it builds this sort of knowledge of each image. So say, okay, when I've seen, if this image has this, and I can see this object, then it's going to be boat or dog or cat. Okay, so basically Google did this and applied this methodology to, apply their resources and this methodology, and they trained a convolutional neural network on over 1.2 million images over 1,000 categories. So this is a type of supervised learning problem because given a specific image, we've got the label, right? We're saying, okay, that's a boat, we want that boat, okay? Let's go and learn. So the conclusion, how good are neural networks? So the downside of neural networks is they have very long training time because of their procedure and the backpropagation algorithm, and we have to iterate over all the training examples. But with a growing amount of computing power and already the applications we have seen, neural networks will undeniably play a positive role and can be applied to so many more things, I think will make a positive impact. Thank you.